In this lecture, we're going to talk about mass spectrometry fragmentation patterns of carbonyl-containing compounds. Here we have 2-pentanone. 2-pentanone has a molecular ion of 86, but we also see peaks here at 71, 58, and we see a significant base peak at 43. So we want to figure out what's going on with those. Of course, one of the non-bonding electrons from 2-pentanone is going to be one of the ones that is ejected. So our molecular ion is then going to look like this. It can then undergo cleavage to release a methyl radical, which corresponds to our peak at 71. If it cleaves the other way and the propyl group comes off, that's going to correspond to our peak at 43. And here's our molecular ion at 86. If the methyl group falls off to form methyl radical, we get the peak at 71. And if the propyl group falls off to give propyl radical, we get that base peak we're seeing at 43. Here's our peak at 43, and here's our peak at 71. However, we still don't know what made that peak at 58. The peak at 58 resulted by something called the McClafferty Rearrangement. In the McClafferty Rearrangement, our molecular ion removes a hydrogen from a gamma carbon. If you don't have a gamma carbon, this rearrangement can't occur. So here's our alpha carbon, here's our beta carbon, and here's our gamma carbon. Let's follow the electrons. That pi bond there becomes the oxygen-hydrogen bond. The carbon-hydrogen bond here becomes the carbon-carbon pi bond. And the carbon-carbon bond here becomes the carbon-carbon bond over here on the right. This enol radical cation species corresponds to our peak that we see at 58. The take-home message really, though, for carbonyls is that we're going to see a peak representing the carbonyl and everything on the left, and a peak representing the carbonyl and everything on the right. We also see the McClafferty rearrangement peak, but it's not super significant, and the most important ones are the two that we have listed up here. Now let's take a look at pentanoic acid. Pentanoic acid also sees a little bit of a peak at 60 here from the McClafferty rearrangement. And for carboxylic acids, you'll actually notice that that's fairly significant. We're not even seeing the molecular ion peak that would be down over here somewhere at 102. So that McClafferty arrangement is much more important for carboxylic acids. We also see a significant peak here at 73, and that is loss of an ethyl radical. Here are some common fragmentations that can help you figure out what's going on when you're looking at a max spectrum. M-15, right, that's loss of a methyl radical. We have M-29, loss of an ethyl radical. M-43 is loss of a propyl radical. And M-57, loss of a butyl radical. M-18 is loss of water, and this is what we typically saw for alcohols. And then we also have our McClafferty rearrangement down here. It's hard to predict, obviously, because this depends on the particular molecule, but we see this commonly for ketones and aldehydes, and it's just M-X, where X is some sort of even number. That concludes this lecture on fragmentation patterns in mass spectrometry. Please review the study guide and the practice problems, and let me know if you have any questions.